Okay, so welcome everyone again. I'm Jorge Contreras, and I will be leading this session about exploring the key question for PV project utility scale plant optimization. So, well, my personal profile, I'm Jorge Contreras Panero. I'm Spanish. I'm a technical advisor for Iberia markets here at RatedPower. And my background, I'm industrial engineering, specialized in renewable energies and a PV design expert. Right now, my current role is to be technical advisor, what means to be focused on customer success, especially for the Spanish-speaking countries and customers, and so to be aware that our clients get the most out of our software, which is PV design. So feel free, if you have any question, go to the question box in the webinar, and if you have other questions and you want to reach me out, you can have here my email, and I will reply your emails whenever I could. So talking about PV design and RatedPower, we have developed a quick tool to optimize the design of engineering and utility scale PV plants as quick as possible and automate. So this is the agenda that we are going to be following for this session. The first point is why optimizing PV plants on early stages, what makes an optimal prospection, some optimization strategies, our conclusions, and a Q&A session that we will have for the answers of your questions. So the first point, why it's important to optimize PV plant on early stages. So as always, time is money, and the optimization and design process is crucial to be really short, and it's really important to bear in mind that we want to reduce the total investment in our projects as well as increase our profitability, but not only in the early stages, but also during the whole life of our PV plant. So that's why RatedPower comes into play and can transform and become this 4-week process that could last into a matter of minutes with our tool. So with the software, we enable the user to have a 360 analysis to make their cost-effective decision in minutes regarding different topics that come into play with a different PV plants designing process, which could be the energy yield, grid connection, OPEX, civil configuration, equipment, topography, or electrical configuration. But here in this session, what we are going to be covering is to optimize the a specific parameter, which is a really important indicator, which englobes every single one in a PV plant design process, which is the LCOE. So by now, this is the important factor that we are going to be optimizing in our designs. So what makes an optimal prospection? First of all, this is a good question because what is the starting point of our optimization process? So an optimization process means that we carry out a specific iterative process where we want to have our LCOE, or levelized cost of energy, as we previously mentioned. Our main goal is to reduce it by keeping the PR, the performance ratio, in such a good level, or even increasing it by installing the maximum capacity for our plant, and so increasing the energy production. So we do so by introducing a sort of inputs into the software, which could be geographical, for example, the topography, the site, the location, and so on. Technical, like the modules, structures, different string configurations, inverters, and so on. And economical, we provide the user to have different templates for the CapEx sheets and for the CapEx calculation. And when we run every single simulation, we follow a closed loop feedback where we get different results in performance and financially meaning. Some of them are the energy yield, specific production, performance radio, and the one we're going to be focusing on in today's session is the financial LCOE, levelized cost of energy. So an important thing to mention here is the software not only provides you the calculation and the different iterations, changing every single parameter, but also it provides you the drawings and all the reports automatically updated and totally ready for different process during the design process. So the strategies that we are going to be following, the first one and the point to start optimizing our PV plant and PV design could be to run a batch designs where. So an important and a simple exercise is to run a batch design and optimization process in the pitch and clearance distance. Why? Because sometimes we have available area, but we don't really know what is the optimal pitch, or even if we can install structures with different pitch, verifying that we have increased or surpassed the power that we are aiming. So one of the specific parameters is to adapt and optimize this pitch in terms of inter-row spacing, for further maintenance works, like having trucks going through the rows, between rows, in order to the cleaning and avoiding soiling losses, and also having a balanced GCR in order to reach a specific capacity or maximum capacity. So reaching this point, let's get down into the software, to the PV design, in order to see how to start a pitch optimization. So as a quick overview, we are seeing right now that this is the software, PV Design, RatedPower, as you well know. And this is the project webinar key questions. And here listed we have all the different iterations and simulation that we have saved and stored for a later view from this my user, for example, or even other teammate that is currently working for the project. So these ones are designs. Let me get down into one design and start working in the run batch simulation regarding the pitch distance. So the first thing, an important thing here in PV design, on the left side, we can see the different tabs that we have for the PV plant customization, which goes from location to cost and settings. And we could step from different tab to another one regarding the specific parameters that we want to edit. But the first and the main one is the site. We need to upload a site. In this specific case, we have uploaded a specific site with an overhead line, a substation, medium voltage lines, and an available area with different restricted areas and an access point. So by uploading this specific file, we are able to run the simulation and detect which is the pitch, the optimal pitch distance for this specific site configuration. We could do so by going to layout and distances, and we could vary this pitch distance in order to go, for example, to 8 meters. We just need to edit and run design. But as we want to optimize the pitch distance, we can run a batch simulation, which consists of a list of 10 simulations varying different parameters. In this case is the pitch distance. So as we have a limitation, which is the clearance distance, we want to minimize this clearing distance until 2.5 meters in order to ease the maintenance works with trucks and semi-trucks during the lifetime of the PV plant. So let me introduce 7.5 meters as a minimum pitch distance to the algorithm, then 0.5 meters step, reaching the 12 meters pitch distance as maximum. And if I refresh this table, we will have listed all the single simulations that the software is gonna run with the different clearing distance. So if I generate the designs, you will be able to see here in the top right corner that we have different results for every single iteration that we have here in the history of designs. As you can see here, you have a level for batch design in order to make you understand that they have been generated by a batch design. So by clicking on each of them, for example, this one, we could get the summarized units for power, energy, and even financial for specific LCOE and total price of the PV plant regarding the different configurations. And we can see also the preview map and the overview of our PV plant with the different power blocks, MV lines, trenches, and so on. So going back to this batch design, if I click on every single one here, in order to make a comparison, I can save these 10 designs and have them stored in the project folder. As you remember from before, this is the project folder and all the simulations that we have run are listed here. So if we want to perform an analysis and compare these different pitches, which is from 12 to 7.5 meters, we could click on every single one of them and compare them together. We could do that by data tables with different parameters like LCOE or PR, specific production, or even by charts. So this is exactly what I did. I performed a charts analysis in our slides. So let me go back to the slides. And after analyzing the results that we get, we could detect that reaching a 56.1% of GCR is a good starting point because we are almost covering half the available area of our PV plant. And with this specific design, we are using a pitch of 8.5 meters. So this is a good starting point, and we are gonna run our simulation on that. So after that, the first strategy that we could assess is to analyze if it is worth it to have a centralized PV plant versus a distributed one. What does it mean? To have only one polygon or even having different polygons to edit to increase editability of our layout. So let's get down again into PV design and see these two scenarios. So when being inside the result of our model, if we go and clone our design in order to edit the different parameters, we will see that we have two different scenarios with different configurations. How do I get here? So an important thing is we have, first of all, if you remind, we have uploaded one single polygon with different elements to our PV plant. But this is super important to have a really well-detailed layout with the different parcels, different polygons, access points, restricted areas regarding the different hydrology of our slopes, and so on. And by doing so, we can increase our layout precision and even create different layouts for different configuration regarding the slopes, for instance. So as you can see here, by dividing in different polygons, we could generate different layouts, different roads, internal roads, structures, deployment, and so on. And we could better adapt to the terrain regarding, as I mentioned, the slopes, the available area, the different parcels, and the different restricted areas regarding the hydrology. So we have generated here the centralized plant versus the distributed one. So if we go again back to the project folder, because we have saved them, and we analyze these two scenarios, having a centralized plant versus a distributed one, if we compare them, in terms of LCOE, we can detect that although we have lost a little bit of available area, we have slightly decreased the LCOE, the levelized costs of energy, although we have exactly the same rated power. This is a good approach because by doing so, and let me go back to the presentation, we have slightly reduced the LCOE by decreasing only 0.4 percentage of available area. But on the other hand, we have reached a higher editability of our parcels. We are considering the different terrain slopes and also different elements such as medium voltage trenches, lines, and so on. So yeah, this is a good approach to distribute our PV plant. The next strategy is regarding the complex orography. As you can see here in our PV plant that we have done, is a complex orography because it's mostly south-facing, a south-facing plant, and our previous analysis had reached 39.46 euros per megawatt hour. So let's run another analysis, but with a complex terrain. So this is crucial to perform a topography analysis in order to generate different platforms or even make an adaptive terrain ondulation and place all the structure adapted to the terrain surface. So we have by default the option given to the user to start using the Google Earth database for topography, but still we could increase the precision of this database and upload our own database. So we are going to compare these 4 scenarios, Google Earth versus an imported one, in 2 different situations. So again, coming back to PV design and to the design process, if I duplicate all the results. Here, an important thing that comes to play is the terrain surface. So for this specific case and scenario, we have agreed that the distributed plant is a good option to move forward. But then we could start generating platforms. How? Because when we create our site, as I mentioned, the topography is automatically uploaded by default via Google Earth, and we have it ready here in our designs. So as you can see here, we have the different slopes and different terrain ondulations regarding the Google Earth model. With this information, we could perform a topographical analysis, which is removing structures which seeks specific limits. In this case, as we want to create platforms, we are going to apply a north-south strategy, and as well as we have most of the slopes facing to the south, this is important to apply only in this direction. So when we apply this north-south topography analysis, what we will get is a list of platforms. Okay. So these yellow structures are referring to the platforms that the software has generated for the different limitations between, for example, for instance, here we have structures that have been installed until 15%, and then between 15 and 20%, the software has applied an earthwork and has created different platforms. So this is a good approach, but the second thing that is important to bear in mind is to have a well-detailed CAPEX sheet. Why? Because by default, as well as Google Earth, if you remind, PV Design uses a CAPEX sheet by default provided by IRENA, which is the National Renewable Energies Institute. So by using this CAPE sheet, we have to add different values and different rows in order to get civil works into the calculations. So that's exactly what I did. I add some different values and prices for the cut and wall and field volumes, as well as LV and MV trenches, internal roads, and so on. And by doing so, we could adapt our calculations regarding the topography analysis to the LCOE and include them. So this is the platform we generate by doing north-south platforms earthworks, but imagine that this is a great amount of ground to be moved and to be worked on. So maybe it's better to have a ground adaptation. Instead of creating different platforms, we provide the software a specific threshold between 100 and 300 centimeters in order to place those structures, and if the software is not able to place those structures between 130 and 300 centimeters, it's gonna create different platform. This situation decreases a lot the amount of earthworks, and as you can see here in 3D Google Earth Maps, the software is still calculating a little bit of different platforms, but still much less than the other situation. So imagine, and let's pretend that we have done this simulation, but still this is a complex orography, and although we are having quite good result in LCOE, we want to make it much more precise. So this is where our own topography comes to play, because another option is to upload with XYZ coordinate system our own topography database. So that makes that our model precision increases, and it enables us to have a much better resolution in these calculations, and so in the LCOE and different parameters of our PV plant. So at the end, we could reach the last example, which is adapt the terrain ondulation with our 3D model that we have uploaded. And as you can see here, indeed we have a much more precise model, because the main difference between Google Earth and this specific model lies on the grid that it uses. For instance, the Google Earth, it uses 25 by 25 meters, but the model I have uploaded is using a 2 by 2 meters grid. So that's why. So if we want to compare these four specific models, we need to go back again. We have saved them, and if we go back to the project folder, we can make this comparison, fair comparison regarding the platforms, the ground adaptation in Google Earth, and platforms and ground adaptation in the external provider topographical data. And if we compare them, that's exactly the data that we have in our slides in the presentation. Summarizing, we have seen that the lowest LCOE has been reached by using ground adaptation, but in Google Earth. But if you take a look and you see that the second one is the ground adaptation, but in our own topographical data, that means that, okay, maybe if we go back again to slides, maybe it's worth it to have, with this different on-terrain ondulation, to have a much more precise and accurate topographical model, because by increasing this grid between 25 meters and 2 meters, we have reached a precision of 37.5%. So maybe this difference in LCOE is worth valuable. So yeah, it depends on the situation. If you have a totally plain terrain, maybe it's not that worth it, and you just want to have a filter whether a plant is available or not, depending on the topography or depending on the available area, and you don't mind about the topography. But when you have complex orography, it's worth it to have a precise one. So a third one strategy to follow is to use much more powerful models and power up your plant. Right now, for the previous designs that we have been running, we have been using 550 watts peak models, which led us to have almost 35, 36 models per string, and this made us to have an odd number of models per string, which makes the structure to be longer, and also if we want to have shorter structures and reduce this number of models, which are automatically calculated by PV design, if we reduce this number of models, we will have inverter input losses. So otherwise, if we go for a much higher and bigger module, we will have a higher open circuit voltage, and that means that we will have less models per string. This is a good choice in order to create shorter structures, and so having an even number of models per string. So let's go to this simulation and compare these two scenarios. As you can see here, PV Design is a cloud-based tool, and whenever I want to enter and log in, it's easy to access and to share all the simulation and the results with my teammates and contact partners. So this is specifically if you remember, the ground adaptation with our own topographical data. We have reached 40.75 euros per megawatt hour. But imagine that we want to use a different equipment, because at the very beginning of our studies, we have used this specific model, which is a Trina Solar with 550 watts power. But imagine that I want a bigger one, the model which is slightly bigger. So it's that simple to change the model and select the one that we are using right now, 650 watts peak. And by doing so, and to make a fair comparison, in order to compare with the previous one, the ground adaptation with our own topography, we are going to do the same, but with bigger models. And yeah, as you can see here, we have increased with this model, we have decreased the number of modules per string, and so the recommendable value has decreased to a value between 28 and 30. That makes you use different structures, because you can use different, for example, in this case, a specific case, we are using a 2V tracker with 90 modules. We can have 3 strings per structure. So by doing so, we have decreased the number of modules per string, and so reduce and shorten the structures. So again, if we go back to the project folder after saving our designs, we could compare both designs regarding the ground adaptation with our own topography and powered up our model, but with as well with ground adaptation and topography. And here is we can clearly see that although we have decreased a little bit the rated power for our PV plant, we still have almost the same peak power and almost the same DC-AC ratio, but still we have reduced a little bit the LCOE, and we have significantly increased the performance ratio, the specific production, and the energy yield. So this is an important summarize, and that's why we highly recommend to use as bigger module as possible in order to reduce our LCOE while using trackers. And here you have a list. So the last but not least strategy is to assess a little bit about using trackers versus using fixed structures. So why is important to make this analysis? Well, first of all, doing an analysis regarding these two type of structures, everybody knows that trackers prove their system and they have better energy yield and specific production. But what if I tell you that, for example, in my case, in my scenario, I have clear south-facing slopes, complex orography, and I have a small and tight tolerance for my tracker manufacturer. So I cannot deploy the different trackers for the majority of the points of my PV plant. So maybe it's worth it to analyze and say, okay, maybe to have fixed structure is worth it because I have shorter structures. The axial direction is not to the north and to the south, either is facing east-west, and so we will have better slope tolerance because, as you can see in the image, the structures will adapt perfectly to the ground, and we'll also be able to adapt a little bit the pitch depending on the south-facing slopes. So if we go to the simulation again, we could perform this analysis, but I have to say here that this is not an easy analysis. Why? Because right now we are not performing a fair comparison. Right now, what we are doing is, okay, let's understand our terrain. Our terrain is mostly south facing, and with this structure south facing, fixed to be. Our terrain, it's mostly south facing, and with these slopes, we could perform an analysis in order to determine a little bit what is the pitch, the optimal pitch regarding the slopes, as you can see here. But this is not a thing that we can perform right now in PV design because it's quite difficult to understand the pitch regarding the slopes in the software. But still, as we have done a PV plan with different multiple parcels, we could reach an agreement and say, okay, the pitch distance optimal for the fixed structure could be at least a similar one as used in the trackers, by consider that most of the slopes are south facing, so we could decrease the distance between rows. So after doing these iterations and considering that, okay, this model, if we perform topographical analysis, we can see that almost no structures are affected by the terrain undulation. This means that we haven't performed any earthworks. As you can see here, an important button that we highly recommend to use is the documentation button. Here, after saving or running any single simulation, we can generate the different documents that automatically generate the software. And one of them is the bill of quantities, where we can account of the number of cubic meters that we have applied for our plant in order to perform earthworks. So here we can see that for this strategy, by using only fixed structures, only 414 cubic meters of land have been removed and have been filled to perform the earthwork. So the dilemma here is, okay, if we have the earthworks to the lowest, but we have increased with the topography analysis the length of every single pile because we have apply a threshold in order to determine the software to apply the structures until a certain limit, maybe the price and the LCOE could be affected, not because of the earthworks, but because of the length of the piles and the steel. So yeah, this is a good approach. And the third one could be, okay, if I go to a fixed structure, what if I decide to go with east-west structures? This is a new trend to perform your PV plant, which is applying to direction fixed structure oriented to the east-west in order to apply and increase the maximum capacity and so the GCR. But the only problem here is that we are having right now a south facing with over 15% of slopes in this terrain. So maybe it's a good choice to maximize the peak power, but as you can see here, the specific production has decreased drastically. So as for now, it could be a really good solution for the ones who are looking for PV plants installing in flat lands and easy different terrains. But for terrains as we are seeing right now, it could be a good solution, but the LCOE has also increased drastically. So going back to the slides, the summary and the conclusion of this webinar could be the next one, which is for sure, if you are using PV design, try to use BAT design in order to optimize your pitch distance. And so your starting point is going to be really good, and a commitment between the installed capacity and balance ground cover ratio. Then if you go to different parcels for your PV plant, be aware that your LCOE is going to decrease with your available area, but still it's a good point, because by having the distributed plant, you are making the most out of the software algorithm. So for sure, go for distributed plants. Then if you go for an analysis, topographical analysis, and you have complex topography data, we highly recommend you to have both our Google Earth topography data, or even to upload an own one. But what you will notify here is you will increase your LCOE a little bit, but you will improve up to 37.5% your earthworks precision calculation. So this is a good approach as well. And then when you have different models and strings configurations, do not hesitate to power up your plant by using powerful models, because it will shorter your structures. And no matter if you have shorter structures, they are going to be much more easy to be placed into the ground, and so this is gonna reduce the LCOE at maximum. And finally, for the racking system, this is a controversial question. Whenever you can use trackers, because it's the better way to get better energy yield results. But should you have any difficult and tight topographical restrictions, go for fixed. And in this specific case, you will have to perform so many iterations in order to get the most optimal configuration for your fixed structure model. But still, this is a simple example. This is not a general way of performing an analysis in PV design. Every project is different, and no matter what strategy you are following, the important thing is, as I mentioned, iterate and perform a closed loop feedback in order to get better results and better optimization of your PV plant. And after that, we have reached the Q&A session. So as I mentioned, thank you very much for attending. If you have any question, please feel free to add them in the GoToWebinar control panel, and I will be reading them and try to answer as many as possible. So thank you very much again. I'm gonna check the questions if there is any of them. Okay. So one question here, thank you very much for the question. In the cut and fill comparison, have you factored the extra amount of steel needed to perform this analysis, or simply install more steel? Yeah, this is exactly what I mentioned. Thank you very much for your comment. This is exactly what I mentioned. When you perform a 3D model analysis, and then you have the topography analysis, if you decide to go to the solution of without earthworks by increasing the piles, the length of your structures, that's why I didn't analyze the LCOE, because I didn't add any parameter in the capex. So if you let me go back to PV design, if I go here to cost, as I mentioned, I have created a specific capex sheet, including general parameters and including the civil works. But still, I could have generated a specific model, adding a new row, a new unit regarding the piles. For example, let's say that this is vegetation, this is the pile length. So regarding the pile length, we could edit the units and calculate the different unitary prices, or even steel uses for the calculation, and we could have done this analysis, but on the other way around. So yeah, I haven't calculate and factor the amount of steel, but you could perform it as I did with the earthworks. Do you always need high resolution for topography? This is a good question. No, a good resolution for topography is for sure not needed, because I personally think that the Google Earth one that we provide in PV design is well detailed, is enough detail in order to perform an early stage analysis. But should you have any occasion, as we are seeing right now, that we have a lot of slopes, complex orography, different hydrology lanes, etc., it's worth it to spend a little bit more time to perform this and to have a high accurate model for the topography analysis. Another good point of researching is, okay, what if I tell you that the mean separation between each poles in the model is 4 meters? So a good approach could be to generate a topographical data model with a grid of 4 by 4 meters in order to be aligned a little bit with the structures. But this is a good question. You don't really need it. With Google Earth is more than enough to perform your analysis. Do you know an alternative platform like IGN? Yeah, this is a really good question. For those that are pretty interested, here when using the software, or if you are not using the software but you want to reach out, we have a specific knowledge base. I can send you the link, which is all the different articles and frequently asked questions on how to perform different activities by using the software. And one of those is how to import different data from Italy, for example, which is in Italy, and in different markets. For instance, in Spain, we have the National Geographical Institute but still in Italy you have Tinitali topographical data, which is exactly topographical data, how to import GIS raster data. And here we will have all the information about how to import it, how to create the model, and so on. I'm gonna share the link of the knowledge base for those who are interested to see those articles. The other one for French is, if I don't misunderstood, is GeoPortail. Exactly, import French parcels inside PV design using QGIS. And those articles are available for the ones who are wondering to have this. Can we have this recording? I think that this is gonna be published via internet, maybe in LinkedIn or even in YouTube. So be aware of our nets and social media in order to get this recording. Okay, let me see other questions. Okay. In this feature of additional ground grading, 3D cabling and terrain following trackers, drag and drop option. I don't really understand your question, but I guess this related to the software. So let me quickly introduce this tab for equipment. For PV models, we have a wide list of different models with different manufacturers and so on. And this is total, well, you have almost 429 different reference, but should you have another model and it's not listed here, it's super easy to go to equipment here, and then you will have the same list of manufacturers and different models, and you could upload your different PAM files for the models, for the inverters, even if you have central or string inverter, and for structures to determine the different structures, you could upload them as well. So I don't know if it is the question, but it's something related. So yeah, I think I have covered almost every single question. We have a bunch of them. So now I would like to thank you for attending to this session. Thank you very much for your time. Be ready because we are going to be launching so many webinars regarding other topics, and feel free to reach me out again if you don't have my link. This is my email in order to reach me out via email if you want. And that's all. Thank you very much for attending. Thank you for your time, and have a good day. Have a good afternoon. See you.